I'm going to talk primarily about epistemological uncertainty. I'm a sort of philosopher of science, sociologist of knowledge before I'm an engineer. So I'm going to talk a bit about uncertainty and its implications for technological failure. And I'm going to do most of that in relation to sort of jetliners and reactors, because that's what I know. But I think the underlying point that I'm using them to illustrate is pretty generalizable, right? So I will try and extend that out to AI and software in the end, right? So talk in five basic parts, right? I'm going to begin with some very sort of brief philosophy of science, not too much, I promise. And then I'm going to argue that this about the limits of to what we can prove. And then I'm going to argue that this implies some accidents are unavoidable. And then I'm going to argue that there are circumstances where this really matters. And then I'm going to look to civil aviation and sort of unpack how it manages to sort of transcend these limits. And then, as I said, I'll close by talking about AI and its implications, wider implications of the argument. All right, the limits of proof. Yeah, if there's one sort of defining problem of the modern sort of philosophy of science, is this really interesting problem that the only thing that we can sort of really satisfyingly prove in a sort of formal sense is that we can't actually prove anything else. Yeah, there are all sorts of names associated with this, Gödel, Wittgenstein, the mid sort of beginning of the 20th century, then Thomas Kuhn, people like Paul Feyerabend, and a whole bunch of others verging out from the sort of 60s and 70s. Saul Kripke, a whole bunch of people. Yeah, and there are many sort of articulations of this problem and different ways of sort of getting at it too that I think are enough, certainly for our purposes. What I'm going to call what is called the Duhem-Quine thesis and the problem of relevance. So one slide each or two slides each, I promise. So the Duhem-Quine thesis is basically this idea that we can't test our theories about the world without relying on other theories, right? So, for instance, any experimental claim is premised on the theory that the experiment has been performed correctly, right? So if a kid at high school comes and says that they've measured the boiling point of water and it turns out that it's actually 102 degrees and the science is wrong, you don't say, wow, the science is wrong. You say, well, no, you've probably got your thermometer touching the bottom of the glass, or your water's not pure, or you're not at sea level, or there's a whole bunch of ways in which the experiment might not be properly performed, right? So that's the Duhem-Quine thesis, right? And there are always sort of chains of theories underlying any sort of claim. And then this is compounded by the next thing, which the problem of relevance, which is essentially a way of sort of getting at the idea that we can't actually be sure that our experiments are being performed correctly. Right? So one way of thinking about the problem of relevance is that the world is potentially infinite, but our representations of it, our abstractions, are what we would capture in an experiment, are always finite, right? So yeah, back to sort of the boiling point of water. I mean, we think that water, sea level, pure water, boils at 100 degrees, but I mean, we can't be absolutely certain we've identified everything significant, right? So turns out all sorts of other random things affect the boiling point of water a bit: surface tension, vessel geometry, and who knows what else there might be, right? So we can never be absolutely certain we're performing our experiments correctly or representing all the things that are relevant to the experiment, hence the problem of relevance. Yeah, and these seemingly sort of esoteric dilemmas have some real world ramifications for engineering, I would argue, have argued. And certainly all sorts of implications, one of which at least relates to how we understand failure or reliability or safety or security. So yeah, we can understand claims about a technological system's future reliability or its safety or its security as theories about the world, right? Just like the boiling point of water or anything else, right? And just like the boiling point of water, again, the uncertainties about the theories, the tests, the models by which your system are known are uncertainties about its failure behavior, right? So you can't be absolutely certain you understand how a system works, or it applies to software just as much as hardware. And in those uncertainties could always lie the possibility for accidents. And if you look at the accident record, which I spent a lot of time doing, you actually find accidents that sort of, I think are best explained by the sort of limits of what we can know, right? I used to call these epistemic accidents. Turns out publishers don't like the word epistemic so much. So rational accidents, which I would define as accidents that occur because a technological understanding proves to be unsound, even though there were rational reasons to hold that understanding before the event, right? So sort of a hallmark of these accidents is that the sort of the tests and analyses of the system in which they occur miss what turn out to be critical flaws or critical properties, because those tests and analyses embody flawed theories about what needs analyzing and testing and how it should be tested and analyzed, right? So the same principles if you don't know that you have no theoretical reason to believe that vesicle geometry is going to affect the boiling point of water. You wouldn't necessarily test the boiling point with different shaped vessels, right? And you see this quite a lot, right? So I tried to find an example from software in honor of my audience. And I think without having studied it super closely, I would argue that probably the 2012 Knight Capital meltdown fits this description, right? So as far as I understand it, what happened in 2012 was software engineers at Knight Capital, big investment firm, updated their servers and used a feature flag labeled RLP for an update. But on one server, right, one server that hadn't been updated, RLP was already a term that was in use, right? And it was still mapped to an old test function in the legacy code base. So when they enabled or told RLP to set it to true or to go or whatever, this old test system started up and started trading, and they lost $440 million in 45 minutes, and it bankrupted Knight Capital, right? And their tests didn't capture this because they never occurred to them that this was a thing that they would need to look for, right? So of course they tested their update on the servers that they thought would be active, but no one ever thought to test this redundant server that had an old bit of legacy code on it. I think who would you blame in that circumstance, right? There's no reason. It's a perfectly understandable error in many ways. Again, it's not something that it's definitely not a mistake that should happen twice, right? I'm absolutely certain that capital firms, look for this now, lest they go the route of Knight Capital. But in that moment, you can very forgivable error in many ways, right? And then there's another sort of property of rational accidents, right? You can kind of you see how they occur, but you say, well, it's really hard to blame anyone. Certainly the first time it happens, right? That's important. And so the sort of interesting property of these accidents is that they're unavoidable, right? In general, right? Any specific one might be avoidable, but you can never be absolutely certain that you've captured every uncertainty in your your knowledge base, your understanding of the world, or the analyses, the tested through which you've derived it. So you can never be absolutely sure that your understanding of a system is perfect. So on some level, you're going to get these accidents, right? And so it brings me to part 3. Where does this matter, right? Because this doesn't always matter, right? So, clearly most of our stuff works most of the time, right? This clearly isn't a massive bulwark to successful engineering in the world, or useful science, right? But I would argue there are some real contexts where this property of systems or this really does start to matter, right? And I think one of the sort of clearest is where it's not the only one, as I'll come to at the end, but certainly I think one of the most straightforward is is when complex systems have to be ultra reliable. When I mean ultra reliable, I mean, the astonishingly reliable. I'll give you some figures in a minute, but and they start to matter in this context because even very obscure uncertainties can become relevant when you're considering what might happen over billions of hours of service, right? Which is the kinds of reliabilities that you make claims about when you talk about sort of jetliners or reactors and a whole, really, really dangerous things that we build. So yeah, when complex systems need to be ultra reliable, and when we need to know their reliability or their safety prior to their use, right? We wouldn't build reactors unless we were confident they were safe. Japan almost lost Tokyo in the Fukushima disaster. Um, and yeah, so this is important because when we need to know their reliability prior to deploying them, then we're inferring their behavior from our abstractions, from our tests and models, rather than inferring it from service experience, right? So, yeah, and of course, these two properties tend to travel together, right? So, yeah, when you have to be absolutely sure that something is reliable, then it's normally because it's very dangerous if it fails, and then also it tends to be the case that you need to know that before you use it, right? I can't think of any case of a technology that has to be very, very reliable, but you can kind of figure that out as you go along. Um, yeah, so for instance, when we build new nuclear plants, this is something I've studied for a while. Yeah, authorities, so the Nuclear Regulatory Commission, for instance, in the United States, or the Office of Nuclear Reactors in the UK, calculate that those plants have a sort of mean time to catastrophic failure of 1 million years, right? So 1 million years of operation, you'd expect one meltdown, basically. Now, it, epistemologically, this is absurd, right? This idea that you take something with as many elements as a nuclear reactor, with all its many complicated operations and materials and processes and the kind of stochastic political environment in which it operates, and then say I've done loads and loads of calculations and I'm so certain that I understand how it functions that I can say that we won't have any accidents any more often than once in every 1 million years. That's not if you're an epistemologist, that's like saying you've invented sort of perpetual motion or something, right? Yeah, these kinds of claims ought to be impossible, right? The just in principle, we can't build you shouldn't be able to build complicated things this safe or know them well enough to make that claim, right? And I can say that about nuclear reactors because, yeah, the data certainly don't doesn't disprove this, right? And the vast majority of systems that demand this kind of level, this order of magnitude of reliability, and there aren't very many to be honest. We don't build them in huge numbers, right? So there's maybe 184 nuclear plants in the world with maybe 400 reactors spread across them, right? Even if one had never melted down ever in the history that in the 60, 70 years that we've had nuclear energy, that wouldn't prove that their claims were correct, right? Because you just haven't gathered enough service data. And of course, we have had nuclear meltdowns, right? We've had several. In fact, I would argue that Fukushima is probably well understood as a rational accident, right? The Fukushima failed at the end of the day because the tsunami overwhelmed its flood defenses, right? Its flood defenses weren't built for a tsunami of that height. In fact, they weren't built for a tsunami of a third the height, right? But if you look into the reason why that was, it's because at the time when Fukushima was built, the seismology in the world didn't recognize the class of earthquakes that caused the tsunami, right? The sort of 9.1, 9.2 earthquake that caused the tsunami that flooded Fukushima. They just didn't think it was possible back then, right? That wasn't a recognized category of earthquake. And then after it was sort of recognized, nobody thought that it was possible in the sort of area where Fukushima was, right? You can remember when Fukushima was designed, sort of plate tectonics weren't really a sort of standard paradigm, right? The seismology's come a long way since Fukushima. So yeah, I mean, they built it for what they thought of as well over 2 to 3 times they built their flood defenses for 2 to 3 times what they considered to be the maximum tsunami height, and they, of course, that same assumption was folded into all their tests, right? When they tested it for tsunamis, they test, well, what if it was twice as large as we thought it was possible, and then Fukushima was fine. And when Fukushima happened, people said, well, it wasn't designed for an earthquake of this magnitude, right? Which is fair enough, but yeah. So I think a rational accident is probably the best way to sort of understand that, right? Um, yeah, but there is one technology that we build in very large numbers and operate, 20 hours a day around the clock. And yeah, the one complex system that we do operate is jetliners. And jetliners are astonishing things, right? There, if you're an epistemologist, jetliners absolutely achieve the orders of magnitude of reliability that shouldn't be possible from in systems of this kind, right? So yeah, think of what jetliners are, right? They consist of millions of sort of elements, parts, complex materials. They're built to sort of fine tolerances. The largest ones weigh hundreds of tons. I think an A380 weighs up with almost 600 tons when it's fully loaded. And so we take these gigantic things, we fill them full of explosive liquid, we loft them high in the air, and then we bring in a unpredictable stochastic operating environment, and then we bring them back down, and we do this millions, tens of millions of times a year, and with astonishing accuracy, right? With astonishing safety. There are 26,000 jetliners in service. They perform over 40 million flights a year, and the whole losses per million departures is 0.06, right? And then if you think that the FAA understands jetliners as basically constellations of about 100 safety critical components, and each one of those safety critical components has to be 100 times more reliable than the system itself. That's an astonishing level of reliability of each of those systems, right? So. Yeah, jetliners are amazing things that just should not be possible. And so this sort of was what I've spent the last decade sort of writing about. This is why my book has a jetliner on the cover, right? So question becomes, well, why and how, right? Why so few rational accidents, right? Why are they not failing more often? How do we pull this feat off, right? So that leads to part four, what I call in the book the aviation paradox. And yeah, when you start looking at this, I mean, ostensibly, the way in which we establish the extraordinary reliability of jetliners is the same way that we do reactors, right? Actually, it's sort of derived from the way in which we do reactors. And that is by testing and modelizing and modeling, not modelizing, modeling and assessing them with they have this thing called the type certification process, which is, well, for American aircraft, Boeing basically is performed by the FAA primarily, and European, Airbus by its sort of European equivalent, EASA. And it's called the type certification process. And it's a gigantic undertaking, right? The enormous number of calculations and tests and models. It's hard to exaggerate just how big this undertaking is, right? So for a new wide body jetliner, certainly one that isn't a derivative of one we have now. So you get the 700 after the number. Yeah, certifying a new jetliner today would cost somewhere in the region of $2 to $3 billion. It would involve upwards of 20,000 staff, half of them, the administrators, FAA and such like, and half of them sort of manufacturers. It would take somewhere in the region of a decade. It's an enormous undertaking, and it's calculative, right? So the idea is you figure out objectively what the reliability of the system is, and it involves huge number of tests. But when you get really close to it, it's clear that this doesn't. I'm sorry, I didn't realize that that was going to play sound. It's clear that this doesn't add up, right? Sorry, it's playing sound at me, so I'll change slides. Yeah, it's clear that this doesn't work. I derailed myself with the sound. Yeah, hopefully that's not playing static at everyone like it was me. Yeah, get close to any
John,
of the tests that they perform,
John,
and these tests are messy.
We can
things,
barely
right?
hear you.
So one of the tests that they perform, what I've got here is a bird ingestion test, right? Where they fire a chicken into a jet engine to figure out if it's resistant to bird strikes. And again, the closer you get to this test, the more you realize that whole communities argue about whether a chicken is pure, actually representative of a real bird strike, and whether it should be fired at the speed that an aircraft is traveling when it's taking off or when it's going at full speed, or and all tests have these properties, right? There's loads and loads of disagreement and uncertainty, people arguing, right? The idea with amongst all these arguments that actually they've got it correct enough to get to a place where they're absolutely confident the jetliners are going to fail no more than once in every billion hours is the figure that they use, just isn't plausible. So and in practice, I would the behind this massive calculative effort, I would argue that the way civil aviation got to these extreme reliabilities is actually much more sort of pragmatic and has more to do with sort of craft tradition. Very basically, very straightforwardly speaking, I would argue that it exploits this facet of rational accidents that they're enlightening, right? That once they happen, we can learn from them. There's no real reason for them to happen again, right? So, and it leverages that, and again, very simply put, I would say that the reason that jetliners are so safe is that we've basically been refining the same common sort of jetliner paradigm for 60 to 70 years, and we've slowly and painfully learned from experience how to prevent it from failing, right? And that sounds straightforward, but I would argue that again, when you start to unpack that making that work depends on three sort of core practices or conditions, right? And I'll call these recursive practice, design stability, and permissive service. All right, so recursive practice. Recursive practice is basically a sort of history of science way of saying that learning from experience, right? Learning from failure, which seems straightforward enough, but actually, again, making this work for them, very, very difficult, very costly undertaking, right? It involved extensively interrogating failures, right? We have these organizations like the NTSB is the most famous, the American one, that will investigate plane crashes at enormous expense, right? To the extent of dredging oceans or picking through forests and piecing together planes, all at the taxpayer expense, to sort of derive why this thing failed, right? And so that they could be sure that it won't happen again, right? And they go beyond even failures, right? They try to collect not only accident data, but data from failures that don't happen, near misses and close calls, right? Mistakes that pilots make, or glitches that could have been ignored, but and there's a huge amount of effort that goes into that as well. A lot of sort of thought about how to design organizations so that people will report things that might otherwise get them into trouble, mistakes, and so on. So in the States, NASA runs that because they wanted to separate it out from the FAA, which has a more sort of policing sort of function. They have something called the Aviation Safety Reporting System. Yeah, and the airlines themselves have parallel efforts. Huge amounts of money and effort and thought goes into interrogating failures. And it's not just interrogating failures, that you also need apparatus for making sure that once you learn, these lessons have been learned, then they are then implemented not only into future designs, but also into existing fleets, right? And this, again, once you start to unpack it, is actually a bit more complicated than you might say, than you might think, right? Because organizations are, unwilling often to spend money on very rare things and so on, right? So, the FAA kind of leads that effort in the States. All right, so that's recursive practice. But then, when you're talking about these accidents that occur, when you're talking about these accidents that occur, sorry, these very, very low probabilities, you're often talking about very, very specific properties. And so yeah, they tend to be associated with very specific configurations of materials or shapes and so on. So yeah, they in order to really kind of consecrate these lessons, really to leverage them, you have to not change your design very much, right? And one of the sort of things that I think has contributed massively to aviation safety is we just don't change planes, right? The planes, to a massively sort of counterintuitive degree, are have extensive design commonalities with very minimal deviation, right? Clearly planes have changed over time. They got longer and wider, and we're aware of things like fly-by-wire and new composite materials and new avionics. But yeah, the fact that we're aware of fly-by-wire and composite materials speaks volumes, I think, right? And these innovations were adopted very, very gradually. Decades after the military aviation adopted them, they tended to be adopted with redundancy for years at first, right? So when we put new avionics in, at first we double them up with redundant sort of classic avionics that we're more familiar with. Composite materials, we started introducing them into less critical parts of the jetliner first. Very, very slowly. They really dragged their heels for ages adopting things like composite materials, even though they promised massive savings. And you can see this you can see this just in the silhouette of jetliners, right? So from 1903 to the Boeing 707, that was 55 years past, right? But the Boeing 707 is recognizably modern, right? So absent the engines, which kind of went through their own design kind of revolution, you'd be hard pressed to tell that apart from a sort of modern jetliner, right? So if you compare that with the 777-9, which is supposed to be coming out next year, so they're clearly very, very similar, right? And so more time separates the second two than the first two, right? Which is kind of astonishing to me. And this isn't because we've perfected the optimal shape of the jetliner, right? There are lots of ways of potentially improving jetliners that would, in theory, make them much more efficient or fly much faster so blended wing body designs and stuff. You see these sort of jetliner of the future concepts all the time. There's a reason that they never materialize, and I would argue that it's for the reason that I'm talking about, right? But it's not just the overall sort of silhouette of the aircraft, right? This commonality, this design restraint runs right through it. You can even see it in the belt buckles, which haven't changed since the dawn of the jet age. The belt buckles that we have are they were introduced in the 50s, I think. And they're exactly the same across Boeings and Airbus and there's just a small token of a much, much wider sort of phenomenon. All right, so when I make this claim, people always say, well, what about Concorde? And sure, I would not deny for a second that Concorde was a radically innovative design, right? Concorde was a significant departure from the common airframe paradigm as we understand it, right? So when you try to make jetliners fly faster, there's a lot of sort of knock-on effects for that. You need new materials and you need new configurations, you need all sorts of stuff, right? The Concorde was a radical airplane. And Concorde, in most people's memories was a pretty safe airplane, right? Concorde flew for 27 years and it had one fatal crash. So yeah, what about Concorde, right? So my argument with Concorde is yeah, you have to understand it statistically, right? There weren't many Concordes, right? There are only 14 Concordes ever entered service, and the ones that were in service flew far fewer hours per day than your average jetliner, right? They spent a lot of time sitting on the tarmac. So Concorde in its 27-year lifespan accrued about 90,000 flights, right? Compare that to the Boeing 737, which accrued about 232 million flights, right? So, and when you adjust for these numbers, right, if the 737 had been equally reliable on a per flight basis, it would have crashed 2,578 times over Concorde's lifetime. Whereas it, in fact, actually crashed high double digits, maybe 100 times, depending on how you define things. And if you did it on a per flight hour basis, it would be significantly higher again, about twice as high. Yeah, Concorde was fantastically unreliable, and I understand that small numbers can be deceiving, but when you look again closely at Concorde, there are a lot of near misses. It's clear that Concorde's failure wasn't completely anomaly. And unless you think that Concorde, to give you a sense of just what an engineering feat Concorde actually was and how much thought went into it, compare it to its Russian counterpart, the sort of Soviet knockoff, the Tupolev 144 or Konkordsky, as it was known. Yeah, Konkordsky was astonishingly unreliable. It was withdrawn from service after 7 months and 55 flights, and over this period, it fatally crashed twice. Yeah, they just could not make it work at all. Yeah, it was an absolute testament to the importance of design stability, I guess. All right, so that leads me to the last sort of pillar of this sort of tripod, and that's permissive service. Right, so in order for this recursive practice to work, even with design stability, you need a lot of data, right? You need a lot of lessons from which to learn, right? So so a lot of service and permissive. I mean, you have to be able to put up with a lot of failures, right? If you're going to slowly hone your airframe design, then you have to be willing to tolerate the fact that it was going to fail quite a lot. And yeah, the history of aviation was remarkably less reliable than it is today, right? And that unreliable history I would argue, was a necessary condition for its highly reliable present, right? It wasn't couldn't have just short-circuited it, done a shortcut. Like, we haven't mastered the art of analyzing systems so much as we've learned slowly and painfully learned the art of building a very specific configuration of what a jetliner is, and we've learned that very slowly over time, right? You can see that in the accident statistics, which go down steadily from 1970. And if you look for charts like this, they tend to stop around 1960, 1970, because if you extend it out any further, that line starts to go exponential, right? You need a sort of logarithmic y-axis, and this just looks flat. Yeah, flight used to be astonishingly unsafe. And if you look at if you speak to aeronautical engineers these days that work in civil aviation, they talk in terms of their history, right? That we don't do this because of that. Every design choice, it has a sort of history to it, and a lesson or a crash or an insight, right? Well, we found that the wheels come off if we have that we don't reinforce them here, and so for all these reasons, the jetliner is incredibly conservative. Right, so you got these three processes all kind of working, and none of them are dispensable. Yeah, and understand that all of these processes, they themselves were relying on quite unusual sort of structural kind of economic conditions and wider conditions, though beyond which I would argue they probably wouldn't have been possible, right? So if you want to understand why the federal government or national governments are willing to spend millions, tens of millions of pounds, dollars, dredging oceans to figure out why jetliners fail, well, I think the end of that sort of chain is essentially the fact that powerful people fly on jetliners, right? Rich people fly on jetliners. They don't have their own separate sort of mean of transport, right? That was an important condition, I would argue. I mean, sociologists are cynical, but the civil aviation benefited massively from the existence of military aviation. It provided this extensive test bed for new technologies with a much higher risk tolerance than civil aviation could ever bear, right? And so we tried out fly-by-wire, we tried out new composite materials for decades in military jets, long before we brought them to civil aviation. And then this weird, again, quite unusual facet of civil aviation where, and I think this is actually diminishing today, but in the past, even a perception of unreliability could kill manufacturers. Very, very rarely do we get a technology where we're willing to punish them enough for failures that they actually kind of go bankrupt, right? So when after Deepwater Horizon, BP made good profit the next year. I'm sure it was record profits, but we find that was the biggest fine we've ever fined anyone, right? But in civil aviation, if your jetliner gets a reputation for being unreliable, people stop flying on it, and airlines start saying, advertising, saying, "Well, we only fly Boeings," they just don't buy your next model, and then. If you're an airframer, every time you introduce a new jetliner, you're pretty much betting the company, right? So there's a kind of litany of jetliner manufacturers that just died for this reason, right? The McDonnell Douglas is the most famous, right? The DC-10 got I would argue, fairly deserved reputation for being a bit less reliable than its peers. People didn't want to fly in it. When they built their next model, the MD-11. Nobody bought it, and McDonnell Douglas went bankrupt and were bought by Boeing. Similar thing happened to de Havilland at the very dawn of the jet age, right? Airframers really care about unreliability, about plane crashes, right? It's very there's a lot of incentives working in the right way, right? Especially because we fly jetliners often enough where if they are unreliable, that tends to manifest fairly quickly. I'm a little bit conscious of the time. Right. So I'm gonna rock on, talk about AI briefly. Now, what does this imply for AI, right? So our abstractions, our tests, our models, our simulations, our calculations will never be perfect. And in some contexts, this matters, right? And it matters, as I've just been talking about, especially when requirements are very demanding, because very obscure conditions become relevant when we need to be very certain they won't occur. But also they matter when systems are deployed in very large numbers, because if you've got a billion iterations of the same system out there, then of course very obscure conditions become relevant then as well. And they become relative when the systems you're building are highly innovative and push the limits of expert knowledge, right? If you're doing something that is challenging people's understanding of materials or design or whatever it is, right? The complexity, and it's very different from anything you've done before, then of course these accents are going to loom a lot larger. And I would argue that AI has all these properties. AI is clearly innovative in ways that push the limits of our understanding and make it very difficult for us to sort of analyze. We're deploying AI very widely, right? There are kind of, God knows how many billion iterations of GPT out there. And increasingly, it's accruing capabilities that imply risks and thus very demanding requirements, right? So, insofar as AI is capable or will be capable of hacking nuclear codes or providing, easy baked recipes for anthrax, then we need to be very certain that it won't do those things, right? Because, A, they're really bad, and B, there's going to be a billion people out there that might, try or have the innovative thought about how to make them do it. AI sits at a weird corner in this stuff. I think the idea that we could ever be certain enough of AI to make those kinds of claims doesn't seem very plausible to me for these reasons, right? I just don't think the epistemology of how we would know that just doesn't stand up. Um, yeah, where does that leave us, right? Well, first of all, I mean, I think we need to keep that in mind, right? It's very easy to forget the limits of our analyses, especially when dealing with extreme numbers, right? So yeah, our intuitions don't scale very well, right? So we don't think of things that need to be 10,000 times more reliable as 10,000 times more difficult, but you know, we should. Um, yeah, so we keep in mind the limits of our knowledge. Um, yeah, I think in general, you know, we underestimate the limits of our knowledge and the risks of innovation. I think we underestimate the value of recursive practice and design stability, and we underestimate the organizational costs and commitments of pursuing those things, right? Yeah, I mean, it is possible epistemologically to exceed the limits of our abstractions, but it requires that we commit to learning and commit to limit innovation, and we operate at scale, and we tolerate failure on to a large degree. Um, and to the extent that we can't commit to these with AI, and I don't think we can on most of them. Certainly we operate at scale, but I don't think we could ever commit to not innovating quickly or um, yeah, well, I think we need to accept that failures are going to occur, whatever our efforts, and um, plan accordingly. What that looks like, I couldn't tell you. Maybe you could tell me.